of the dielectric response is given in this way. And so we have the static dielectric, the high frequency dielectric matrix, plus the term which depends on oscillator strength and on the frequency of the light, omega, and the frequency on the vibrational mode. And this formula permits also to calculate the static dielectric constant. We just have to put 0 here, and we see this is very similar to the formula that we have introduced. The imaginary part is given in this way, which is similar, that we have a spectrum which is localized. We consider here infinite time life, so delta, so infinite small this spectrum, in which we have peaks corresponding to excitation on the same frequency of the vibrational modes. Well, this is imaginary. So we can calculate the real imaginary part of the dielectric function in the dielectric response. So now, just to give some other formulation, that in most experiments, I just consider first this, that's more important. So in most experiments, what they, for example in FTIR, what's reported is that is the absorption spectrum. Once you calculate the imaginary and the real imaginary part of the response that we've done before, you can calculate the absorption spectrum just with this formula here, just in which c is the speed of the light, so compared to the spectrum. And also, is often reported the energy loss function along one direction, and this is given, can be calculated by taking an imaginary part of the inverse of the dielectric matrix at this frequency omega, and also can be calculated using this formalism like this. And for calculating this frequency, the oscillator strength, you have to consider the vibration calculated along the direction. Okay, maybe can be a bit abstract, and I just wanted to give an example of what these spectrums look like. So this is just what we've done some time ago. This is a model of gaseous material. It is found also using quantum espresso with Carparinello molecular dynamics, which is something that you will learn next week. Okay, this material is formed by these planary units, which some way forming also these rings like this. Okay, this is how we can. I think there will be some example like this in the next week. So to calculate a model like this, we start from a crystalline structure. And you will see it's possible to simulate, to heat up the structure and to simulate the liquid of this material, and then we simulate in very fast time scale the formation of a glassy material. So we quench it, and this quench is just 6 degrees. The spectrum that I wanted to show is this. So this for a complex material is how the real part of the electric constant in the infrared is, and here is how the imaginary part. So this value here corresponds to the static dielectric constant, and so these two lines, the blue is the experiment, and our simulation was the red line. And here is the energy loss function. Just to say the shape of this.
What's the difference between the red and the blue line?
No, the red is the theory and the blue is the spectrum. So
The theory from the quantum pressure calculation or from the dynamic molecular dynamic calculation?
No, the molecular dynamic calculation was used to calculate the structure, and then we used this formulation for calculating the spectrum.
But it's 2p corresponds to usually in the
because if you in this material, we have a big in the density of states. We have that the most of the the vibrational density state is quite it's not localized on a lot of peaks, but this is the most the peaks that are more coupled with the electric field are along these two frequencies. Okay, just okay. Now, so you've seen how to calculate infrared spectrum, and now we consider another spectroscopy which is very widespread in the lab, and it is called Raman scattering. So in Raman scattering, we are using, in this case, light at frequencies which are higher than the frequencies of the vibrational modes, and there is a process which is like this. We have an incoming photon which has frequency omega L and polarization EL, and this photon is scattered into another photon which has a frequency which is the difference of frequency. This is outgoing photon, which is frequency, which is the difference of the frequency of the incoming photon, but with respect to the frequency of the phonon, which in this case is created. And then we measure the polarization of the outgoing photon. So this is called Stokes process. There is also possible another process in which, instead of creating a phonon is annihilated, and in this case the frequencies of the outgoing photon will be the frequency of the incoming one plus the frequency of the phonon which has been annihilated. Okay. Also in this case, because of the big difference with respect to the wavelength of the visible light and the size of the primitive cell, if you want, only phonons near the gamma point contribute to this process. The difference with respect to the momentum of the two phonons will give the direction of the Q vector of the phonon that has been created, and this can be used then to simulate the spectrum at certain precise angles with respect to the incoming and outgoing photon.
Why only long wavelength photon will be responsible? Gamma means long wavelength photon, right?
Yeah.
Why they will not be responsible? Why not the
Because
short wavelength photon has higher energy, long wavelength photon has lower energy?
yeah, but
Why they
if
will
you
not be responsible?
because it depends on the frequency you are using. Because you usually use visible frequency because you don't be in the frequency that can be in the wavelength of the photon is comparable to that of the crystalline.
The frequency of the light is of the order of a few electron volts, so that the Q vector of the light, both incoming and outgoing, are very small. So the difference can only be very small. So the light is, the speed of light is so fast that the corresponding Q vector is basically zero. And so this is why you only sample the zone center and the scattered light.
Now we consider the non-resonant limit. No? This is so we consider the specific case in which the frequency of the light we are using is lower than the frequency of electronic excitation. And in this case, the Raman process is in the so-called non-resonant limit. And this is we report here the cross section. This omega here is the solid angle, that's the volume. for the Raman-Stokes process in the non-resonant beam. Stokes process, so if a phonon is created. So the cross section looks like this should be a power cross section. Looks like here. So we have a Raman tensor R, which depends on K, and K is the vibrational mode. Here can be written like this. We have a factor which goes as the frequency of the scattered light, the power of 4, no? Which is the power of an oscillating dipole. V, in this case, is the total volume of the sample. Then, this alpha K is the Raman tensor, proper Raman tensor for the chi vibrational mode. Here is the frequency of the mode. And then we have a boson population factor. Boson population factor of the population factor for phonons at the frequency omega. This also explains the difference, the why Stokes modes, so the modes corresponding to phonons that are created, are much stronger than lines for phonons that are created. Indeed, what's happening is that if you want to annihilate a phonon must be present. So what's happening that in the form for anti-Stokes process, you don't have this factor +1. This factor is quite small. So what's happening that the Stokes process in which phonons are created are much gives origin to Raman lines which are much higher than for anti-Stokes processes. So usually Stokes is measured. No. So now we have to see how the Raman susceptibility, because Raman susceptibility or proper Raman tensor are calculated. So this is a tensor with the 4 indices, with the 2 indices for every mode, vibrational mode K, and we just have to take the derivative of the electric susceptibility at high frequencies with respect to the atomic displacement. This is the main ingredient. And then we have to multiply it to the atomic displacement. Sorry, here I have should be a factor K here relative to the vibrational mode K. I can do this for every vibrational mode, so I can calculate Raman stabilities for every vibrational mode. This is the definition. So just an example, another vitreous material also obtained from first principle. And here is what this is looking like. So this is a Raman spectrum. This is how for disordered materials or liquid spectra are usually in the configuration which spectra are usually measured. Is H means horizontal with respect to the plane of scattering, and vertical means which are vertical with respect to the scattering. This means HH means that so in the experiment the incoming light is horizontal with the plane of the scattering, and also the outcoming light is measured with the polarization measured at the polarization which are horizontal to the plane of the scattering. HV means that so the incoming light is horizontal to the plane of the scattering, and the outcoming light which is measured with a polarization filter is vertical. And then here is the two spectrums. This line here is the experiment, and the other is the theory. It was just to show the different two, the difference between this part here and this part here is that usually in works what is reported is we just drop these terms here. So this in the bottom figure, we calculate all the spectrum. In the upper figure, we just report this term here and this term here. Sorry, just report this term here, which is called the reduced Raman spectrum. Okay. Okay, now we've seen how to calculate infrared spectra, we've seen how to calculate Raman spectra, and now we want to calculate the spectra from cross-space, possibly using the quantum espresso. So, you remember that we had introduced an Hamiltonian, we introduced a formula for the energy of the system, which was coupled with the macroscopic electric field. So, what we would like to do is to couple the electric field. We study an Hamiltonian, which can be also many bodies, in this way, which is the Hamiltonian when there is no electric field, calculate this with the density function theory, plus a coupling of the system with the electric field, which can be written like this. No? This is just on the static theory. The problem is that the position operator is not compatible with periodic boundary conditions. So we don't know how to treat the direct and non-Hamiltonian like this. Okay. So there are different possibilities to solve, to deal with this problem. So the simplest case is that suppose that we are to calculate the infrared spectrum and the Raman spectrum for an isolated system, for example, for a molecule. No? So we know that in our code we use periodic boundary conditions, so that this would be a problem, but in this case we just have a molecule. And here, indeed, the solution is quite simple. We could use a sawtooth potential. No? Sawtooth potential, which is linear like this. So this is my periodicity of my cell. No? It's linear in one part of the cell that then goes down, and then it's just periodically repeated. So, well, around the area occupied by the volume occupied by my molecule, a sawtooth potential can simulate a macroscopic electric field. And this is a good solution. It's also implemented in quantum espresso. Then, the solution is that of using linear response. Then we'll see how we don't have this problem linear response. And also, the linear response problem is very analogous to the KP perturbation theory that we'll see in just in a while. And then it's also implemented in quantum espresso on the final electric field method, also to couple with the macroscopic electric field, and also to calculate all this matrix set. So I will not speak further of the sawtooth potential, but I will speak just a bit about linear response, just to give the lead. So here, let's suppose that we have a Hamiltonian like this. So this the Hamiltonian operator, which is the Hamiltonian without the coupling electric field, plus just the coupling electric field, which is just written. X is will be just considered one Cartesian direction for simplicity, and lambda is the magnitude of the coupling. Okay, now we can span everything in with the Taylor expansion, both the energy this way and both the wave function. The wave function in general here we can take either the one particle wave function or many body wave function will be just another. Okay. What's happening is that at first order, let's suppose this is just a many body wave function. So we can rewrite the first order as a sum of all the states which are different from the ground state. And here, and so we have to decoupling. Don't know how to treat. Enter just between the ground state and the state which is different from the ground state. So, which is just right then the term like this. We don't know how to calculate in this form here. So we just consider the commutator of the Hamiltonian, region Hamiltonian, without the electric field term, with the position operator along one direction, and then we have then we have to a term which is as the difference of the energy with respect to the state. But now we know now how to calculate this commutator term, which is nothing else than the momentum operator plus another term that appears in the code, and this term is due to the fact that we are using pseudopotential, and all the pseudopotential implemented quando espresso as a non-local term. So we also have to take of the non-local term. Okay. This is how we can. This is the reason why linear response does not have this problem for treating macroscopic electric fields. Okay. Now, you know that so this we can linear response can calculate easily the electric thing, so we can calculate Born electric charges. But for the Raman, we have to consider a third order derivative now of the energy with respect to twice the electric field and once the atomic displacement. No. And now this can be a problem with linear response. Indeed, there is a general theorem which states that suppose that we want to perform higher order linear response approach. This theorem states that if we know the wave function till a certain order n, this will determine the derivative of the energy up to the order which is 2n plus 1. So we don't show how to show that this is true. This is based to the fact that at all order the wave functions must be orthonormal. And I think that all of you know already used the simplest version of this theorem, no? Because at order n equal to 0, the 2n plus 1 theorem takes the name of this is just the Hellman-Feynman theorem, if you want. Then also you can show, you can demonstrate it from induction in a very similar way. So this means that we want to calculate for the Raman these tensor, which are third order derivative of the third order derivative of the energy with respect to the electric field and atomic displacement. We just need to know the first order wave function, derivative of the wave function with respect to the electric field or with respect to the atomic displacement. And this has also been implemented in the quantum space. Yeah.
On the slides before you showed pretty much like high-level perturbations theory.
Yeah.
So you implicitly assume the Born-Oppenheimer approximation.
I think that Born-Oppenheimer approximation enters how we define the phonos. Phonos we define Born-Oppenheimer approximation. I think it's like this.
So what was the question?
The formulas in the slide before, it's like stationary perturbation theory. So is it then that
yeah, but this is in fact this is the reason why these are the formula for the non-resonant Raman spectroscopy. I think that in the case of resonant Raman spectroscopy, in which electronic excitations are involved, I think nobody really knows how to formulate. I mean, for non-resonant case, you are in a regime in which the light does not excite directly the electrons. So Born-Oppenheimer is still valid.
You have very high energy for 200 milliV.
200 milliV is small. He's saying 200 milliV, that's still small.
200 milliV is still smaller than the gap, typical gap. I think the main point is that if it is off resonance, then the amount of electronic excitation is small, so you can still neglect it, let's say, at least first order.
Yeah, just for finishing this part I started this one. Once can ask where the momentum, the form momentum has gone. Indeed, the form momentum and all the analytic part of the dynamical matrix are important for things that when we want to calculate the frequency of the phonon, for example, if we want to reproduce the Raman scatter experiment in a vitreous material, it's important to calculate the dynamical matrix along the direction which corresponds to the direction of the exchange momentum in the experiment. And experiments are reported for transverse and longitudinal. Second, just in certain cases, in the Raman formula, another terms is appearing, which is close to the modulation of the light by the tensor, which is the second order susceptibility. Not really for this, but in certain cases it is important for the scale longitudinal. Okay. Now we've seen how we can calculate 2n+1, and then finally we introduce the fine electric fields, which is also very connected to the methods used in the talk by Nicolas Paul for calculating the polarization. So the idea is that we want to minimize a function which is called electric enthalpy function, which is the term. No? So we have seen the same formula we have seen before, which is the function of the wave function. We here we indicate as with the psi, the many value wave function we see just in a while y, and the electric field. This function will be given by the total energy of the system with at zero macroscopic electric field, plus a coupling that we've seen before will be just the polarization times the electric field. Okay. Now, in essentially 15 years ago, was been produced, published a theory called the modern theory of polarization, which gives a formulation for obtaining expectation value of the polarization also in periodic material. The polarization, here we write along a direction alpha, is written like this. So psi here, just I give here the mini body with the many body formulation. Here we have the psi is the many body with function. We have to take the expectation value with respect to this operator, i.e. alpha, where G is nothing else than 2 pi divided by L, and L is the length of the orthorhombic cell. We just suppose here that we are doing calculation with just one big supercell, so just at the gamma point. So we are using a cell, orthorhombic cell, and the edges have lengths which are called L alpha. So G is just this number like this. And we note here that this EIGR operator is a many-body operator. So we to take this number, we take the logarithm, and then to take the imaginary part. And then we have to multiply. So this omega just to give a polarizability instead of the dipole. And then here we have to extract the factor and multiply by the length n. Okay, this was a theory that has shown that it is working, and let's see how this theory is then implemented with the density functional theory. So in density functional theory, our many-body wave functions are nothing else than Slater determinant, and so an expression like this, where EGR is operator EGR, expectation value of this operator calculated with respect to many-body wave function, as we are using a Slater determinants, the determinants of the Kohn-Sham eigenfunction, is becoming the determinant of a matrix S. In this matrix S, we have to consider for each single, for each Kohn-Sham eigenfunction phi I and Kohn-Sham eigenfunction phi j, we have to consider this term. So we construct this matrix X, and then we consider the determinant of the matrix, and this permits to calculate the polarization. Now, this formulation can be easily generalized to key points, and it takes this formula like this. So we have that the space of, first of all, we have to take a measure of key points which are equally spaced. It's important for the calculation of the very space. And then here, let's suppose that we want to calculate this alpha is on one direction. We will have a measure of key points, which is written like this as parallel, which is key points on the direction alpha. And you see here, we have to take a product of this determinant of these X matrices. In these X matrices now, each point K will just be coupled with the following key point along this parallel direction. So in this sense, we form strings of key points. And then we have to sum over all the strings. We have to sum over all the sorry, this logarithm must be so here logarithm must be so we have to put this logarithm inside here. Then we have to sum over all the strings which are parallel each other. So we have to sum over them. So the key point which will be orthogonal with respect to the direction for which we want to calculate. Okay. And finally, here how we can use this finite field method for calculating what we need for calculating infrared Raman spectrum. So this will be the topic. The topic of the subject of the exercise. So we have seen that so we can perform now with the code. We can select a value for a direction for the electric field, and we can relax the system with the electric field, either letting the atomic coordinate to relax, either to keep it fixed. Then, when the system, the electronic structure is being relaxed with the value of electric field, we can obtain the polarization of that value of the electric field is what we want to calculate. So let's suppose we want to calculate the Born effective charges and the relative stability by frequency, and also the derivative of the relative stability by high frequency with respect to atomic dispersion. So it's very simple. If you want to calculate the Born effective charges, they are defined as a second order derivative of the total energy with respect to once the electric field and once the atomic displacement, but the derivative of the energy with respect to the atomic displacement is nothing else than the force. So the effective charge will be nothing different than the derivative of the force with respect to the electric field. This means that we'll just to take the electric field in one direction, and then by taking finite difference, we can calculate directly the Born effective charges. The derivative, the calculate, if you want to calculate the relative stability high frequency, we'll just have to calculate differences of the polarization, or if you want, difference of the dipole. That's an exercise. And then let's suppose that we want to calculate the Raman tensor, so the relative stability of the derivative of the relative stability at high frequency with respect to atomic displacement. We just have to calculate the second order derivative of Hellman-Feynman forces, calculated at different value of electric field with respect to ice electric field. So what you do, you select a certain value of electric field, you calculate all the forces for certain value of electric field, and then you can calculate by taking finite differences. You can calculate these tensors. What's interesting is that if you can calculate this number here by this finite electric field made of by linear response, and you see that there are two different behavior on how this number will converge with respect to the key point mesh you are using. So indeed, what's happening that the linear finite electric fields methods converge slower than the linear mesh method. So indeed, you will see this in the exercise. And also in the exercise, I think that the linear response method are I think it's better to use a linear response method if you can. Finally, just brief discussion of the bibliography. So in this work, there is a dynamic of crystal lattices. I've defined the first part of the model. All these quantity of current features are defined. In this work with Andrea, we define we present formalism for the Raman. We discuss a bit the formalism for the Raman. Most of formula for also for the neutron scattering. This paper, like this paper here. So all the big paper for the density functional perturbation theory. And it's very interesting method that here we have not been time for discussing, but a very efficient implementation of 2n plus 1 theorem is described in this paper here for the calculation of the Raman spectrum of the Raman tensor, and it's also implemented in the quantum express. Okay. The Berry phase polarization is described in this paper here, and also in this the first paper of the Vanderbilt group more than 15 years ago. And the finite electric field method are described in these two papers. And I have to say also here a lot of work has been done in the group of Nicola very recently. And there is a work of very recent work of Mustang that I suggest you to read. Maybe I will give you the reference. Okay, that's all.
can pay the break and then reconvene at 11:15. So,
Yeah.
你让他们怎么做 MD 的 calculation？ 你向我答几个问题。
So if you want to extend to yeah.
How to calculate the polar frequency?
No, I think that the same method is working also. I mean, no, let's suppose that we have a nanohour, nanotube or something. Then you can define the polarizability, no, and also the stability in two different directions. One, for example, in the direction which is orthonormal, you can just use a sawtooth, and you can see a lot of how it polarizes. In the direction which is perpendicular with respect to the tube, you have to use one of these methods, is cell volume, but in one slide there was a solid angle. Just for the Rama.
But the cell volume is more or less arbitrary.
Yeah. Well, the E is arbitrary, but then if you have a bigger cell, also you have to consider more vibrational noise and more output. So you have the same amount. Just for the Rama, to say that here in the format, dV is the total volume of the sample. And this is also a power cross ratio in the sense that usually they count phonons, but not regarding the reporting the spectra in terms of sorry, they count photons, and then spectra are reported in terms of how many photons have been counted and known about and out with respect to the energy of those photons. But just here, V is the volume. So usually, accurate measure of the absolute intensity of Raman spectrum are quite rare. Usually, it's just a relative, it's just good spectra, but we and at least for solid, just in a relative unit. Coffee.
Here, if anybody